Good morning. Welcome to the December Vibrant Technology webinar. My name is Mark Richardson, and I am joined by my dad, Mark Richardson Sr. And we're coming from snowy Colorado, and we thank you for joining us on this Thursday before Christmas. Hope you're all getting ready for the holidays. Today we are going to be doing a webinar titled Expanding ODS Data with FEA and EMA Mode Shapes. So we will be getting into that here in just a little bit. A couple housekeeping items during the webinar. Everybody will be in a mute mode. If you do have questions during the webinar, feel free to type your questions in the dialog box there on the right-hand side of your screen, and we'll try and get those answered at the tail end of the webinar. We are recording this webinar, so we will get this posted out to our YouTube page probably sometime next week after Christmas. And so if you want to go back and review anything during the webinar, you have you can go out to the YouTube page and access that. With that, I'll hand it over, and we will go from there. Dad, take it away.
Okay, thanks, Mark. Good morning to all of you. As Mark said, it's a little bit cold here in Denver, but we have some pretty exciting stuff to share with you today. So maybe it'll at least warm up your brain a little bit. This was a description that we put in our newsletter that got you people invited to this webinar that are joining us today. And the red part is the changes, so and the emphasis. So let me just read it to you. As Mark said, the title, we were going to just use FEA mode shapes, but we're also going to show you an example where we use experimental modal analysis, or EMA mode shapes. And the two properties that we're going to really take advantage of today and illustrate with these two examples is that all resonant vibration of a structure is made up of a linear combination of mode shapes. So that's just the fundamental mathematics that we use for modal testing, for ODS testing, for various applications, relies on that assumption. The second one, which many of you, and if you're a vibration analyst or engineer, maybe don't think about, but all modes of a structure are excited at all frequencies. So we're going to look at some of these properties today, look at a little bit of mathematics. Hopefully I won't scare you away with the math. We'll get through it as quickly as we can. We're going to use two examples. The first one is expanding ODS data, experimental data. When we say ODS, operating deflection shape, we've normally measured the surface vibration with accelerometers or with a laser vibrometer or some type of sensor that's measuring the surface motion, acceleration, velocity, or displacement. And then in the second example, we're going to take some experimental data that we took off of a race car, and I know one of you, Jim Steedman from Navcon Engineering, is probably attending, and it's one of his race cars. So we'll take a look at that data, and we'll use that to expand some time histories. So again, you think of a time history or a sequence of time histories as just a sequence of ODS data. It's just deflection data in the time domain. And of course, if you're familiar with Emiscope, we can animate by sweeping through time histories, or we animate by putting a cursor in some frequency domain data and using a sinusoidal animation or deformation of the structure, the test article from the frequency domain. Or when we've gone through curve fitting, we simply display the mode shapes themselves, or some ODS data if we're just saving values at a cursor location into a shape table. These are all the things that we normally do with Emiscope in order to get a graphical representation of the deformation of the structure. Okay, I'm going to go move on here to our operating manual. Now, we have recently made all of our tech papers, our application notes, and our operating manuals available on the internet. You can access them very easily. Now, when you install Emiscope, you get them, but some of you may not be Emiscope users. So you can go read the manual and find out all about Emiscope by just typing in manuals.vibetech.com. Now, rather than do that, I've got a copy of what we call a reference manual. Now, we used to have tutorials in the manual. We've taken them out now, and we're in the process of changing those into application notes, which will have demo project software associated with each app note that you can download. And more recently, we've now, and we don't have it quite done yet, but we have a trial version of Emiscope. So you can actually use Emiscope for 2 weeks, no charge. You can download that from our website store and then download some of our app notes and those projects, and you can actually do what I'm going to be doing here today. And we're also going to include those with our webinar. As Mark mentioned, we're recording this, so the projects that I use in Emiscope will be available with the webinar videos. You can download them. You can get a free copy of Emiscope and try all this stuff out for yourself. So I'm going to go through the manual here, and I'm going to go down, and we're going to look at what this shape expansion is all about. And this is using ODS data, relating ODS data to mode shape data. Let me scroll up here, page 141, something called a participation matrix. So let me click on that, and we'll just read through a little bit of the operating manual here that explains what a participation matrix is. This matrix equates the shapes of one shape table with the shapes in another shape table. So each shape table can contain ODSs, FEA mode shapes, EMA mode shapes, or simply what we call an engineering data shape. It could be temperatures, it could be scalar engineering data that we've acquired experimentally or even analytically. So we're going to define these two shape tables with complex shapes in them. Now, when we say complex, don't let that scare you. It's not complicated. Those of you that have taken algebra and certainly a course on complex variables know that a complex variable or a complex number is simply magnitude and phase. So that's more familiar to most of you. A number that's represented by magnitude and phase, or real and imaginary. Those, you need two numbers to represent a complex shape at each of its components. So we start off by assuming that. And then when we get to FEA, of course, those are just real numbers. We'll talk about that a little more. But here is the math. This is just algebra. This is an equation here that says the participation matrix multiplied by one of the mode shape matrices equals the other one. Now, I said mode shape. These are not necessarily mode shapes. They're just a deformation shape, an ODS that I measure on the surface. Function of frequency, function of time, it doesn't matter. The idea of a shape is that the relative amplitude and phase of each of its components relative to the other components is unique. That's what we mean by a mode shape, or even an ODS, or whatever we're measuring. So here's a little more math broken up, these matrices. Each column in the U matrix is a mode shape or an ODS. Each column over here in the V matrix is the same thing. They got different dimensions based on how many shapes are in each of the shape tables. Now we're going to go down here and actually solve for the participation matrix. This is very simple linear mathematics. This is how you solve a set of equations when you're trying to equate the left-hand side to the right-hand side. and things maybe don't match up perfectly. So you end up with what's called a least squared error solution. Now, in order to do this, you have to invert the U matrix. So this is a little indication here of a matrix inversion. Those of you that are math experts know that that can be problematic. So we'll take a look at that when we get into looking at some real data here. Essentially, what I need in order to do that matrix inversion there of the U matrix is linear independence of each of the columns of the U matrix. And we're going to use something called the MAC calculation, or the modal assurance criterion, because that is a measure of the linear dependence or independence of two vectors. So we can use the MAC calculation, which is a standard tool in ME-scope for comparing two mode shapes or two ODSs, to check out the columns of the U matrix before we do the inversion to make sure things are going to work well. And then we end up with this participation matrix. Okay, so what do we do with the participation matrix? ME-scope has another command in there called shape expansion. Now it's under the tools menu in the shape table. We'll look at some of this as we get into using ME-scope here in a minute. We're going to expand ODSs with a few measurements in them. M-pound is what we use as an abbreviation of a measurement. Using mode shapes with many M-pounds in them. Or you can call them DOFs. Degree of freedom is a measurement. And in ME-scope, we interchange those two words. So columns in a shape table are measurements. Traces, what we used to call traces, now we just call them measurements in a data block. Could be FRF, could be time record, doesn't matter. So we really have two ways to store data in ME-scope, either a block of time or frequency data or a shape table with shapes in it. So we're going to go ahead and this is what we're going to demonstrate today. That the expanded shape over here, this V matrix, the expanded shape, ODS, whatever it is made up of some measured components plus some unmeasured components. So typically in an experimental situation, we don't measure that much data, maybe a few hundred degrees of freedom. And we'll look at a couple of cases where even we have less than that, and then we can expand it with mode shapes that have many more degrees of freedom in them, and we use this participation matrix to do it. So here's for you guys that went to sleep during that math, here's what we're going to do. We're going to take some shapes with many measurements or degrees of freedom in them. We're going to take some shapes with a few measurements or degrees of freedom. Go through this mathematics in ME-scope, and it happens in a blink of an eye with these fast computers now. And we get out an expanded shape, which we will use, and we'll just show it in animation on a model. Okay. What else did I want to show you? There's a, we already talked about the MAC calculation. Now, last month during our webinar, we used two different metrics, one called MAC and one called SDI. And they are both common commands in ME-scope. MAC has been around for many years, was a PhD thesis of a grad student many years ago at the University of Cincinnati. A common way to compare two mode shapes. SDI is more recent. It's something we invented at Vibrant, and it's part of ME-scope. And we used that last month in the webinar to compare sets of measurements. And but I want to go back and just show you a picture of what a MAC value looks like. So MAC is between a pair of shapes, and in this case we've got one shape A, which is just got two components in it, a 1 and a 1, and B, which has variables X and Y in it, and they can vary over a range of values. And this is a plot of what the modal assurance criterion looks like. So MAC indicates the collinearity of two shapes. Well, we're going to use that for matrix inversion, because that means that if two shapes are collinear, they're going to cause problems when we try to invert a matrix with those shapes in them. But if they're not collinear, then no problem. This math is going to work fine. So what this shows is that there's a whole line of values where when the B matrix is lying on that line and the A matrix, of course, is a 1 and a 1, then MAC is equal to 1. But as soon as the B matrix goes off of that line, then the MAC value drops. So it's always got values between 0 and 1. And you can see as we get close to 0, the red area there is showing a very small value of the MAC. So that's a strong indicator of the collinearity. Here's an SDI plot. It's similar but different. SDI measures the difference between the two vectors A and B. So here we got A is equal to 1 and 1 again, a vector with two components, and B is a variable, got variable X and Y in it. And there are only two places where SDI equals to 1. Everywhere else, it's going to be less than 1. So we can use SDI to compare an expanded ODS with the original data. So let's go ahead and do that. I'm going to bring up ME scope here. Let me put this down. We can come back here. Mark didn't mention that during this webinar, if you have questions, you can send them in as a text message, I believe. And so if we finish a little early, we'll have a chance to answer some of those questions that you may have about what I've already said or what I'm going to do here in a minute. Now, this is a project set up, and we have this little test article. It's a little rotating machine here with a belt drive and a motor and a couple of wheels there, and we can put on balance on these wheels, and we can measure ODS data. So what we've done on this machine is we've actually taken live data at 8 locations, and the locations are shown with the blue cubes. And so 8, and these are triaxial, so the cube is indicating it's a triaxial accelerometer. And we just ran this machine at different speeds and then acquired the accelerometer data at 8 locations, 1 on each bearing block, and then there's what, 4, 5, 6. There's one over in the corner, 6 of them on the base plate. Now we also built an FEA model of this machine, but not completely. We just modeled the base plate and the bearing blocks. Now I've got a project all set up here with some hotkeys, and this is a standard feature in ME Scope now in any of the packages, and we call it scripting. And each script has a hotkey associated with it, and you can see there's a bunch of them here, and several of them are indicated with a flaming hotkey, and some are indicated with numbers, kind of just a way to go back and refer to hotkey 1 and 2 and 3, and you see when I put the mouse on her, it kind of has a name to it. So I'm going to just press the first hotkey here, and this is a script dialog box that's coming up. The hotkey is running a script now, and we can't see it, but it's running inside of ME Scope. And I'm going to look at 10 FEA modes of the base plate and bearing blocks. So we're just going to go ahead and start the animation. And here it is. So animation will sweep through the mode shapes. This is again another script dialog box that I added to this script, and I can go in and edit these. So we can go and stop it and change it if we want to. Press the numbered hotkeys in order to display the expanded ODS versus the acquired ODS. So what we're going to do is take these FEA mode shapes, and you can see that the low frequencies, now we're starting to get into what we call flexible modes, but the first 6 are what we call rigid body modes. And it's simply the free vibration of the structure in space. Now, the model we have here has got some springs under it. We didn't model those springs. Those are well, it's a geometric model, and they are simply being animated using the geometric interpolation that's built into Emiscope. So very simple. I add a spring, and the bottom of the spring is fixed, and the top of the spring is following the base plate that it's attached to. So those are very easy to set up in Emiscope, and then the interpolation will deform all the points on the spring from top to bottom. So that's a good graphical description of interpolation. And we use that a lot in Emiscope because we don't make measurements in thousands of points. We only make measurements at a few points, but we want a realistic looking model. So what we're looking at here are the FEA mode shapes, and Emiscope has an FEA solver in there, so very easy to do. And STM, even if I don't use the FEA solver, I can use the mode shapes of one of the bearing blocks and the base plate, and duplicate the bearing block with its mode shapes, and then hook them together. Actually, the way we built this model was we put very stiff springs between each of the bearing blocks and the base plate, because the points don't line up. So you've got to attach them with stiff springs. SDM basically gives you the same answer as the FEA solver in Emiscope. So this is the FEA mode shapes. Now let's go press the next hotkey here. And now we're going to shift over and animate the entire model using a combination of, all right, what's it telling us here? Expanded ODS on left using 2 rigid body FEA modes versus the interpolated ODS on the right. Now, interpolated means that we're using the geometric interpolation between the 8 accelerometers to deform the rest of the model. So here it is, and we even got the parts rotating and so forth. So here's on the left is the expanded ODS. You can see it's a very clean, smooth animation, and this is at what does it say? 985 RPM. So that was just one of the running speeds, and then with this little knob here on the power supply, we can change the speed of the machine to a different speed, and you'll see that and as the model depicts, the machine is simply sitting on 4 rubber mounts as we run it. So those rubber mounts, the springs are depicting how it bounces around on the rubber mounts. The other thing you notice here is that the experimental data is not perfect. It's experimental data, and you can see, for instance, this point here on the back side by the motor control is moving around a little funny. When we curve fit that data with a FEA set of mode shapes, we get a nice smooth animation. So that's what we mean by least squares curve fit of the experimental data with the analytical mode shapes. And over here is the participation. So I've only got 2 modes here, and this is S1, S2, shape 1, shape 2. It's using a lot more of shape 2 than shape 1. Now, those were the mode shapes we looked at previously, and down here is the expanded data. Here's the expanded data at 985, and then below that is the ODS data at 985 that we expanded from. So we could look at those too, but there's just those are just shape tables full of numbers. Let me go. Oh, and here's one more thing here. If I only use 2 mode shapes to curve fit the experimental data, here is the SDI value. It's very low. It's saying 34%. So SDI is saying that the shape on the right, or let's say the shape on the left, is not matching up with my original experimental data very well. Well, the reason for that is I'm only using 2 mode shapes to match up the motion of this machine. So let's go up here and use 6 mode shapes. This button up here says use 6 modes. So I'm going to press that hotkey, and that's going to go in, and all right, it's going to tell me what it's doing. 6 rigid body FEA mode shapes on the left and the ODS data on the right. So now you can see the participation of those 6 mode shapes in this experimental data. Same data on the right, a different expanded shape on the left, and over here the participation, now it's using all 6 mode shapes, but 2 of them very heavily in order to match up to do the curve fit with this experimental data. And notice this, the SDI value has now jumped up to 86%. Rule of thumb on SDI and MAC is that if it's over 90%, that's a good match between the 2 shapes. Now again, we're just matching them at the 24 degrees of freedom, 8 times 3 of the accelerometer locations, the triaxial cells. Let's go a step further then, and this hotkey says use 10 modes. So we're going to use all 10 modes now. 6 rigid body and 4 flexible modes. So we're using this basic physics principle that the ODS we measured on the real machine is just a linear combination of mode shapes. And the other interesting thing is that the FEA mode shapes are real valued. The experimental data is very complex valued, and you can see that in the animation because the machine is kind of rolling around due to some unbalance in the rotors that we added to make it behave in a kind of an unbalanced or a complex way. So we got 6 rigid body, 4 flexible. Let's go ahead and take a look at what that is. So now we can see we're up to, well, 87%. Got a little better on the curve fit or on the match between the expanded and the experimental. And we're still heavily using 2 of the rigid body modes, but all the modes are being used in a different amount. These numbers are just the numbers in the participation matrix. They don't go between 0 and 1. They are the numbers that the participation matrix actually uses to expand the experimental data and get us the nice looking ODS on the left. So this is something we could do with virtually any experimental data once we have the model set up and some FEA shapes. Now I'm going to go to the second key here, and this is a different speed, 1400 RPM. So we sped the machine up a little bit, and you can see that, well, it's not telling me that it's 1400, but the hotkey said it's 1400. And you can see the participation change. See, now we got a different rigid body mode. We actually got 3 rigid body modes, but different ones that are participating in this data at 1400. And the SDI says they're 91%. So the curve fit is even doing a better job at this higher frequency. You can see the linear interpolation over here where the geometric is not real good, but over here we got very nice motion because we've got a very smooth ODS there. Let me go to the next frequency. Now we're going to go to 2200 and some change. Okay, this is, and we're using all 10 modes again. So I can go back and you can use 2 modes, or I can use, again, what we're looking at on the right is just the experimental data with the geometric interpolation. And, you know, we got some maybe not perfect data from the accelerometers, but over here we got a nice clean animation because of that curve fitting. Again, if we look over here in the participation, we're using mostly rigid body, but we're using like 4 rigid body modes now, a little bit of the flexible body modes, not much. compared to the rigid body motion, because this machine is not flexing that much. Even at 2200 RPM, it's really a mass on a spring, just bouncing around on its rubber mounts. And of course, this is exaggerated. 94% though, so the curve fit, as we went to higher speeds, the curve fit got even better using the FEA modes. What else do I have up here? Let's see, number 4 is going to compare the two expanded, we're going to look at the expanded 985 on the left with all 10 modes curve fitting the ODS data versus an expanded ODS on the right. And I think that one's going to be the 2200. So we're comparing the two expanded ODS results now. Nice animation, nice smooth motion. This one on the left is at 985. This one on the right is, oh, it's 1400. The 1400 RPM ODS. But look at the SDI. So what this is saying now, we're comparing all the degrees of freedom, and I think there's several thousand degrees of freedom here in these two ODSs. But they're quite different because the machine is being excited differently between those two speeds. And then I'm going to go to number 5 here, and I think this one will compare the 985 with the 2200 RPM ODS. So once you have the experimental ODS data stored in shape tables in Emiscope, you can do this type of shape expansion. Again, here we are. This one over on the right is 2280 RPM, and the one on the left is 985. And you can see that the SDI is telling us these are completely different expanded ODS shapes for the machine at these two different speeds. So that is what I wanted to show you from this example. Now let's go to a different example. Let me see if I missed anything here. Just a quick review. We can go back. And the nice thing about the scripting and the hotkeys, it's basically programming Emiscope to do the same thing over and over again. So again, we started out with mode shapes that included the free motion of the structure. And those are the easiest mode shapes to get from an FEA solver. They're not typically as easy to get experimentally, although we can usually pick up a couple of the free modes depending on how the experiment is set up. We can pick up the free modes of a test article and add those into our database. But FEA is the best way to get all of the free modes, and you can see they're just here they are. We're sweeping through the animation of each one. I mentioned something else when we were looking at the math, and that is the linear independence of the shapes on the left-hand side of the participation matrix formula that we were looking at, the mathematics. The MAC calculation is a way of measuring that, or at least graphically displaying the linear independence of these mode shapes. So let's, I'm going to stop the animation and we'll just take a look at that. And I'll put the shape table over here in the middle so we can see here are the FEA shapes. Now the curve fitting said nothing about frequencies, nothing about damping, only the shapes are needed to do the curve fitting. And that's a nice that's a nice thing to keep in mind. You know, I don't need to have accurate FEA shapes. We sometimes do FEA model updating to try to match the frequencies between FEA and experiment. That's a common thing that's done, but here we don't need to do it. We're simply going to take the shapes themselves and curve fit them to the experimental data, using the assumption that all the modes are excited at all frequencies. So we just looked at some data at 3 different frequencies, 985 RPM, 1400 RPM, 2200 RPM. And we curve fit this data. Well, the curve fit involves the matching DOS, but the expansion involves all of the DOS. You can see there's 1938 measurements here. Let me expand this a little bit and then we'll zoom it down. So what we were looking at in the animation was expanded DOS with 1938 shape components in them. You can see this data. Well, these are the mode shapes. Now, the mode shapes are basically the phases are all 0. The magnitudes, we don't care. Again, we don't even care whether the units are, and this is typical FEA units for a mode shape, inches per pound. And then the seconds are thrown in there. We won't go into those details right now, but these are what we call unit modal mass, or they are scaled so that if I had a mass matrix and pre and post multiplied the mass matrix, now the FEA does have a mass matrix, then these mode shapes would give me modal masses of unity. This is one of the ways we scale the data. But getting off on some rabbit trails, some tangents here, let me look at the Mach value between all of these shapes. Now it says you got something selected here. Do you want to unselect? I'm going to say yes. And I'm going to compare them with themselves. So I want to compare the FEA shapes with themselves. Now remember, the Mach value is compares a pair of shapes. So what this is doing here is comparing pairs of shapes from the shape table. And the diagonals are each shape compared with itself. So the answer is 1. Obviously, they're collinear. The off diagonals are showing us that these shapes, when I compare one shape with a different one, the answers are almost 0, meaning that they are linearly independent of one another. And you can see here's a little bit of dependence here between shape 10 and shape 4. But the value is still quite small. Actually, it's just showing me 0.114% as opposed to 100%. So those two shapes have a little bit of collinearity or linear dependence, but what we're looking for is just, we want independence for doing that matrix inversion. Now, let me go back here because we're really only interested in the matching DOS. And the matching DOS are at the location of the accelerometers. So let me put this back over here. And, well, I don't have the accelerometers here, do I? Let me see if I have them in this as a substructure, and we'll select them. I'm trying to get this thing over here. Okay, let me see. These are substructures. Let me see, shafts. These are all different pieces of this model that we've created substructures. A substructure is simply a collection of points and lines and surfaces, and they can be anything that I define them to be. So I'm looking through here. Here's one down here called triaxials. So let me hide everything and simply put up, well, let's do this. This will show me everything. Here's the model. I had the rotor kit hidden. And now I'm going to come down here to triaxials, and I'm going to select those accelerometers. Now I'm going to go over here to a command under the measurement links, M-pound links, and down here it says select the measurements. Now since I'm connected up to the FEA mode shape table, that's connected to the model, I want to select, and what it's doing is it's going through, these are the links of all those accelerometers. This was set up in the model previously, and now I want to go over, and you can see, let's go back here in the shape table, I can see which degrees of freedom out of these mode shapes is actually going to be used, and it looks like just the beginning ones, which is what we would expect, points 1 and 2 and 3. We numbered them up to point number 8. So those are the 24 degrees of freedom where the mode shapes must be independent of one another in order to calculate the participation matrix and then do the shape expansion. So let's go back and look at that with the MAC calculation to see if we have linear independence. Now it says, do you want to unselect all M-pounds or measurements? I'm going to say no. And now I'll select the same shape table again because I want to compare all the mode shapes with one another. And again, it's saying, hey, you didn't know whether I picked a different table or the same one, but do you want to unselect? And so here it is. Oh, let me just say no again. That was too many of a reminder. So here is the orthogonality. That's another term for linear independence of these mode shape components. Just for, this is the FEA modes with themselves. You can see up here on the top, FEA modes, FEA modes. That's why we were able to do the curve fitting so easily, because we still are using the mode shape components that are linearly independent of one another. All right, I think I've covered everything, enough mathematics to probably drive half of you away. Let's go and get, I'm going to close this project. So let's close this one, and I'm going to open up a different project. And we're going to use this same, it says, do you want to save? I'm going to say no. And now I want to go, and this one here is called a NavCon 911. I mentioned earlier that NavCon Engineering Network is a company in Los Angeles that does training on Emiscope, does consulting with Emiscope. Been doing it for many years. Jim Steedman is the inventor of a model we use in Emiscope quite a bit called the Jim Beam. And so we use that for a lot of things. But here is a model of, let me just make this larger and we'll take a look at it. This is a Porsche race car. And let's put the body on. So here it is. This is Jim's race car, and this was tested by putting a shaker under it. I didn't do the test. We're just looking at some of the data from the race car. This is a photo model of the race car, but you saw that underneath of it was a stick model. So for doing engineering work, the easiest way to set up these models and to look at, mode shapes and ODS data, your experimental data, is with a stick model first. You can build that in Emiscope very easily. Then if you have some photographs, we offer some software called Photo Modeler that will build a model like this. And but there are other ways. You can get solid models from Google SketchUp and Autodesk. You can take photographs. This was built from photographs of the race car, and you can see there's lots of things on there. I'm going to take the decals Let's see, why are they? Oh, okay. So I'm going to take them off. We'll see when we animate here in a minute that the decals were set up as a substructure, but and you know, here's one up on the front fender that we particularly want you to see. Vibrant is one of the let's say business partners of Navcon, as well as some of these other companies. So let's go back to the stick model and look at some of the experimental data first. So I'm going to hide the photo model, and it's just a little easier to see our data. And I'm going to push a hotkey. Again, I've got 4 hotkeys up here. I'm going to push the first one. And what we're going to see here is some of the modes of this car. Let me get them back here in the middle so we can see everything. There we go. Now these were gotten by curve fitting. If we start with mode number 1, you can see that a little bit strange. And let me put the points on. You can see here's where the accelerometer was located. Most of it triaxial data. If we look down here in the shape table, you can see the triaxial data. But the third mode is what I'd call a suspension mode. Now we're starting to see the true motion of the car. And I've got some points sticking out here in space, point labels, so a little bit crazy. But you can see that there are 4 points that have larger labels on them. Number 70, 79. Let me just stop the animation here for a minute. Because what we're going to do in this case is we're going to simulate an accelerometer mounted out here on the front fender at 0.70, another one over here at 79, and then 2 more in the back here, one at 74 and one at 65. And these are going to be locations where we have time records. So this is a kind of a simulation of, let's say, driving this car on a bumpy road and measuring its vibration at those 4 locations. And you'll see there's just sine wave data. We just made it up, but we're going to curve fit that sine wave data with the mode shapes of this car, the experimental mode shapes. Let me just go back and push the hotkey here, and we'll go back and animate them again, and you can take a look at them and turn this off so you can see them a little better. Even this stick model has a lot of points in it. You can see that there's quite a few points, and we did that so that when we interpolate, first we interpolate the points on the stick model, and then we interpolate all the points on the car model, the photo model, from those interpolated stick model points, and we get a smooth animation that way. So there's a lot of tricks you can do with the geometric interpolation. We're going to focus mainly on these suspension modes. There's the back end really moving up and down. This next mode is the front end moving up and down on its springs. Now we get a couple of torsion modes in here. Now the wing is missing off the back. I have a little problem with, let me just see if I can get it back. I'm going to hide the stick model. Now I've got everything hidden. And I'm going to bring it back. Okay, there's the wing. So the wing came back, and I think there's a conflict between the 2 models. So if we go look at this in the quad view, it's pretty clear what we're looking at here with these various, here, let me get the modes up together. Here we go. So let's go back here. I'm going to click on the first mode. There's a bending, not a bending mode, but a suspension mode of of the car on the back. Now let's go to, there's a suspension of the front. You can see the wing is a little bit crazy. That's okay. We'll just take that data and curve fit it. Now here's what I wanted to show you. If we look at the front of this, for this mode, number 5 is, it's a rocking mode. Now there's a little bit of torsion in there, but it's basically a suspension mode. And here's another rocking mode, but now the wing is out of phase with the car body, whereas if I go back here to number 5, it's in phase. So those are typical things that the animation will show up very quickly from your experimental data. So we're going to focus our attention on those 4 modes, and we're going to curve fit them. Let me stop this and just show you the data that's in a data block that we simply made up. And this is some sine wave data. So let me just zoom out here. You can see there's actually 3 frequencies in this data. There's 12 measurements. So we got X, Y, and Z, but the X and the Y, I just cut and copied these various sine wave time histories, and in the X and Y we've reduced the motion quite a bit. You can see it's a fraction, and up here we got 2 or 3 G's of motion. Now this is in G's. We could easily integrate this data to velocity or displacement. It really won't matter. The shape expansion is going to work with this data, and what it's going to do is, as the cursor sweeps through the data one time step at a time, we're going to curve fit the mode shapes of the car to this experimental data, simulated experimental data. But we're using actual experimental mode shapes of the car to do that. Let me just go ahead and do it. I'm going to push this second hotkey here, and you'll see a whole bunch of things going on together on the screen. So what you're seeing here, and it's kind of flashing, I should have put a little pause in the scripting so we could look at the calculation, but here is showing the cursor versus the expanded. And so this is the SDI value, shape difference indicator. And sometimes it does a real good curve fit, and sometimes it's not as good of a curve fit. Here I'm just using 2 of the mode shapes. So I'm just using the mode shape 3 and 4. Those are the suspension modes. And you can see that primarily they're jumped over. As we sweep through and expand this time history data using the experimental mode shapes, it's primarily showing the car on the back end. Now we're all done, and here is a cascade plot of some of the response of the car. Now, there are all the degrees of freedom of the mode shapes. You can see I've only got a few selected here so that we can look at them, but there are actually 279 measurements that were made on the car. XYZ well, it looks like, just looking at the numbers here, 53 different points on the car body. But let's just go ahead and do a sweep animation of this expanded data to see what it looks like. So I'm going to go ahead and push the, oh, that was the wrong, I think it's the 4th one that I wanted to push. And here it is. Here's how this car, I'll turn off the points here. This is how this car is being excited. Again, simulation, riding over some bumps where we're simply measuring the acceleration at 4 points on the car body and curve fitting the first 2 suspension modes of the car to the time traces. And over here on the right, we're sweeping through 197, however many traces of data we have, and we're looking at how the car itself is responding to the sine wave data. So again, just using exactly the same commands, the participation, the expansion, using SDI to measure the difference between the raw data and the expanded data. How good is the curve fit? I believe that's all we're going to look at today. I can go back and change the number of modes, but we're out of time here. Again, a modal model, whether it's experimental or FEA, is really what you need to get nice, smooth animation of the car. Here, I can turn the, let's go back and I'm going to turn off the decals, but I'll turn on, let's see if we get the car, and then I need to turn off those decals because they don't animate very well. So here is the car animating with a sweep through the simulated sine data. If I come over here and look, you can see there's actually 197 traces of data, quite a bit of data, not too easy to look at here, but it's all being used to animate the model. There you can see where the cursor is lighting up the data that's being used to animate this model. Now this model has 35,000 points in it, so it's quite extensive. Let me just stop that and show you here if we go to the points. And then we'll wrap it up, Mark. Do we have any questions?
No questions at this time.
Okay, well, we have a good audience. Either that or we put them all to sleep. But I wish you all a Merry Christmas. Here, as I speak, I'm going to scan through the point spreadsheet. So we got 34,349 points on this model. And we can animate just fine using 197 or so expanded points on the stick model, and then interpolating the car model from those 197 expanded points. All right. Merry Christmas to all of you. We'll see you back in the new year. We'll probably have a webinar in January, and we will announce the topic. And if you have any questions, any requests, those are all welcome. And thank you for attending today.